vectors and how to add them, right? And subtract them. Today we're going to find out whether they're parallel. We're going to start using vectors. Here, I'll point to the screen. Are they parallel? What's the scalar product of a vector? We're going to find equations of lines, which is kind of goofy. And then something called the dot product. Yesterday I failed mightily in proposing a compelling reason for the dot product, so I might just go straight to that, because it is almost Friday. We'll find the angle between the two vectors. That's what we're going to do. How do you feel? Ready to go? I'm excited. These are parallel vectors. Earth-shattering. What do you notice? What do they have in common? Some go one way and some go the exact different way. Slope is exactly it. How are they different? Yeah, they're different lengths, right? So those are parallel vectors. Are you surprised? No. These vectors are parallel. What do you see? And what's the relationship between 27 and 207? Yeah, they're opposite directions. Oh, by the way, I forgot to really mention the zero vector. The component, or the polar coordinates for the zero vector are 0 and at any angle you want. So my zero vector, I could stand here and face anyway, and it's the same vector. I'm going nowhere. And this is important. It has its own slide. The zero vector is not parallel to anything. I want to add something. Okay, so that's important. That makes sense? How can a dot be parallel to anything? These vectors are parallel. How can you tell? These are component vectors, right? So that first one in the upper left, 3 steps to the right, 5 steps up. You can look at the ratio of the y to the x. Nice. Can you create another one that's parallel? Like if I said 12, you'd say, giveaway, 20. Right. So I took my 3 and I picked a number and I multiplied it. And then you figured out the number and multiplied it. I hope that's what you did. Yeah. Yeah, but it's, however it manifests itself in your brain, that's essentially what you did. That's what the zero vector looks like in component form. 0 right, 0 down. That's what it is. Just to make sure I have it. So here it is. Parallel vectors have the same direction for different scales. So that's called being a scalar multiple. That's why they use the word scalar instead of some other word. It's a scalar multiple. See what it does to the direction? Nothing. So that's the definition of a scalar multiple. Same direction. Farther distance or shorter distance, or maybe the opposite distance. I really feel this 15-minute limit up here. I feel like I have to hurry. Okay. So, 4 miles northwest times 3 is 12 miles northwest. Got it? Easy. Okay, so in coordinate form, both of the components have magnitudes in them. So 5 to the right and 2 to the up, 22 up. You multiply that by 3, they both get multiplied by 3. Where's the direction in component form? Where is the direction hidden?
The ratio.
It's the combination, right? It's the ratio. And you do the inverse tangent of 22 to 5. So you can't see it directly. And if you multiply both the numbers, that ratio, by something, the ratio stays the same and the direction stays the same. I should do a sample problem quick, even though I'm on the clock and only have 15 minutes. Let's see. Do a scalar multiple. Let's do 527 degrees. And let's multiply that by -8. Well, let's take the component vector 611 and multiply that one by 5. And let's take this vector and multiply it by 2. So it's -8 times polar vector 5, 127. -40. Grab your calculator. 127 times 1. Because it doesn't change direction. What if it's in component form? 6 steps right, 11 steps up. Multiply that by 5 and you get 30, 55. And for this one, yeah, you do. So you have that one.
How do you know that?
Got it? When does it get difficult, Mr. Rickman? Not today. Not today. Okay, now, all right, so we have everything we need to come up with a vector equation for a line. And there are people that go, I have y equals mx plus b, and it works great. It's been working since Algebra 1. I'm not going to do anything else. Next week, it will no longer work. Because next week, we're doing lines in 3 dimensions. And what does the b stand for in y equals mx plus b? It's the y-intercept, right? Yeah. I didn't pronounce my b well. Some people thought I said m. The b is the y-intercept. In 3 dimensions, you've got yourself the x-intercept, the y-intercept, and the z-intercept. Where would you put the next intercept? And what does the m stand for? Slope, which is rise over run. We got rise, we got run, we got, I don't know, pushing out towards you, something else. Yeah, back, forward, up, down, left, right. You can't do a 2-dimensional look at an equation for a line, space. So we're going to learn how to do the vector equation of lines so that next week we can actually do an equation of line of any kind at all. That's really easy. Okay, so since it's a vector equation, it's called a vector value function. Everything's a vector. Here's how you do it. If I want to make a line that goes through 6, 3, the first thing I got to do is start at 0 and make myself a vector that goes to 6, 3. What vector starts at 0 and goes to 6, 3?
6, 3.
Yeah. Most textbooks use this for vectors. So that's a component vector. And that's nice, because I can go, here's the point 6, 3, here's the vector 6, 3. I kind of wish I just ignored the book and gone with that, because this book says, here's your vector 6, 3. Okay? And then, we're going to add this vector over here. And that vector is 4, -1 does not get me the line. That gets me the point. But I could add another vector and get another point. I could flip around and add a vector and get a point over there. I could take my vector and make it smaller, and it's not quite where I want it, but that's okay. I get this vector right here. So if I take the vector and make it bigger or smaller, what am I doing? What's that called? Scalar multiplication. Anybody know what it's called? Scalar multiplication? Scalar multiplication? Absolutely. So what am I multiplying to get all the points? Everything. So I'm multiplying by everything. So I need a variable. T. Okay? So my equation is xy is 6, 3. All of this for everyone to see. Don't subscribe. There it is. Okay? So if I want to go in this direction, I just hop aboard a vector that takes me to a point I know, and then I add a bunch of vectors going in the direction I want to go. And that gives me the line. Capiche? Have you seen this before? Is it a physics thing?
Yes.
Is it? It's physics-y. But you never know. Gotta see if I'm explaining it the same way. So there's the form right there. So that's a vector. Right. That's a vector. That's a vector. And that, T, is a scalar. The textbook then talks about something called the parametric form of a line, which so far I haven't seen again. So you take the x component times t of your vector, and then you add it to the x coordinate of your point. It'll come up when you go home. So see if you can try that out. Find the vector equation of the line through the point 8, 9, 6, and parallel to the vector 5, 7. Yeah, it's just, you know, all your x, y's, all your vectors going to points on the line. They're just 8. Go up to 896. And then any old multiple of 5, 7 will get you to other points on the line. Okay? Got it? Any questions? That'll be the end of part 1.